Okay, recording. I'm going to get started. So, basic announcements. Today we're going to finish off chapter 5. Chapter 5 homework is due on the 12th. Chapter 5 quiz is on the 10th. So that's a week from today. The homework is due Wednesday next week. We will have a lab on Wednesday. It will be on heat for chapter 5. That reminds me, I need to send David an email about that, but and so we will have the lab on Wednesday. Okay, so we were talking about the kinetic theory of gases. So gas consists of molecules that are moving at high speed. Independently in all directions, and the higher the temperature, the higher the average speed of the molecules. And gas molecules will collide with each other in the walls of their container. And the distance between molecules in a gas is on average big when compared to the size of the molecules. What this means is that you can basically interactions are minimal. Stuff just bounces off of each other. And if you think about the collisions of billions of molecules with the walls of a container, like this, for example, one of the things you can do, you add more molecules, you get more collisions. There's more force on the container and therefore more pressure. To remove some molecules, there's less pressure, less force on the container. And similar logic can be applied to other things. So pressure is defined as force per unit area. The SI unit is a Newton meters per meter squared. It is a Pascal. There is also an older SI unit from the CGS system that is the bar, which is 10 to the 5 pascals, that gets used a lot because 10 to the 5 pascals, or 1 bar, is very close to 1 atmosphere, which is extremely convenient. So atmospheric pressure is 1.013 times 10 to the 5th pascals. So it's like 1.013 bars. So bars are a really useful unit. Another common unit is an atmosphere. It's the normal atmospheric pressure at sea level in 0 degrees Celsius, which is 1.1013. Actual atmospheric pressure varies. So right now, the atmospheric pressure, according to the barometer on the wall, which reads a little high, is something like 1.025 bar. Let me see if I can get. Sometimes you can actually get the weather thing to tell you what the pressure is. .17 inches of it. Okay, and according to the weather app, it's 1.0122. So that's not too far off. So it's a little higher than average atmospheric pressure, but it's also warmer than 0 degrees Celsius. And, it changes with the weather. And an atmosphere is 1.013 times 10 to the 5 pascals, or 14.7 pounds per square inch. So the US customary unit for pressure is the pound per square inch, or PSI, which you've probably seen on your car tires or on, probably most likely seen it when you're looking at tires and stuff. And if you have a pump, pumps have gauges that measure the difference between the atmosphere and their pressure. Usually. So for example, this one measures unfortunately, it's a million different. This is a vacuum pump. It's measuring in millimeters of mercury, which is also called torr. There are a million different units for pressure, unfortunately. I will not put any unit conversions of pressure on any questions or tests. So pressure and number of molecules. So if the temperature and the volume are held constant, we find that pressure is directly proportional to the number of molecules. You increase the number of molecules, you increase the pressure. You double the number of molecules, you double the pressure. If volume and number of molecules are held constant, we also find pressure is directly proportional to Kelvin temperature. So that's temperature in Kelvin. Well, you need to use Kelvin. You need to measure from absolute zero, so it's actually proportional to like the kinetic energy. The idea is you increase temperature, molecules move faster, they bounce off the walls more often, and they hit harder when they bounce off the walls. That increases the pressure. And lastly, if number of molecules and temperature are held constant, we find pressure is inversely proportional to volume. The pressure is proportional to 1 over the volume. So you double the pressure. Sorry, you have the volume, you double the pressure. Basically, if you squeeze it into a smaller space, that increases the pressure. Because it has to go less distance to hit the walls, is a way to think about it. And so we find that pressure is proportional to NT over V. And we can write a relationship that, P2 over P1 equals V1 over V2 times T2 over T1 times N2 over N1. Now, I included this. On no problems that I give you will, in all the problems I give you, N will be held constant, because just that's how your book does it. So if N is constant, you drop this term. Any term that's constant, you can replace it with a 1. Now, it turns out you can actually work out what the relationship between pressure, volume, and temperature are. And this is the ideal gas law. And the more commonly used one by chemists is PV equals little n big R T, where P is pressure, V is volume. Little n here is the number of moles of a substance, which is easier to measure in everyday stuff. R is the gas constant, it's a constant, and T is the temperature. There's also a version that physicists tend to use, which is PV equals big N, which is the number of molecules, times Boltzmann's constant times temperature, but that's because Boltzmann's constant times temperature is kind of a measure of the average energy of molecules, so physicists like to use that. But this is the one that gets used more often. I just wanted you to be familiar with it. You're not going to actually ever have to use it in this class. but like if you take a chemistry course, you will learn this equation. And so you can see how basically all gases act the same. The big exception you run into on a regular basis is steam, because steam tends to exist very close to its boiling condensation point when you're doing stuff with it. And water has got lots of interaction, so it's ugly and messy. And you're not likely to run into that unless you're doing engineering or something. So if you have a closed rigid container, N is constant. Rigid, volume constant. Holds a particular amount of hydrogen gas. The initial pressure is 1.8 times 10 to the 6 pascals at 20 degrees Celsius. What will the pressure be at 40 degrees Celsius? Well, we can take this. We know volume is constant and N is constant, so we could replace those terms with ones, and we get P2 over P1 equals T2 over T1. If we solve for P2, we get P2 equals T2 over T1 times P1, but we will need to convert from Celsius to Kelvin. So when we go from 20 degrees Celsius to 40 degrees Celsius, we are not doubling the temperature. We're increasing the temperature by, we're going from 293 Kelvin to 313 Kelvin. So we multiply by 313 Kelvin over 293 Kelvin times our initial pressure of 1.8 times 10 to the 6 pascals, and we get a final pressure of 1.92 times 10 to the 6 pascals. You go up by a few percent. So here we have a closed container. Closed means N is constant. It contains 2 liters of nitrogen gas at 1.1, 1.01 times 10 to the 5th pascals at a temperature of 300 Kelvin. If the volume of the container is decreased to 1 liter while the temperature remains at 300 Kelvin, what is the pressure of the gas? So we're starting with 1.01 pascals in 2 liters, and we're squeezing it down into 1 liter. So what happens to the pressure of the gas? I'll give you a couple of minutes to work that out. Well, we start with P2 over P1 equals V1 over V2 times T2 over T1, because that is constant, so we can drop that term. But the temperature doesn't change here. Starts at 300K, ends at 300K. So we can drop the temperature term. So P2 over P1 equals V1 over V2. So P2 equals P1 times V1 over V2. P2 is 1, thus P2 will equal 1.01 times 10 to the 5 pascals, that's P1, times 2 liters over 1 liter. So it will come out to be double, 2.02 times 10 to the 5 pascals. Half the volume, double the pressure. So we have a closed container containing 10 liters of helium gas at 1.01 times 10 to the 6 pascals at 300 Kelvin. Here, pressure is going to remain, oh no, to what volume? So here we're changing volume. So what volume must the container be increased at constant temperature to achieve a pressure of 2 times 10 to the 5th pascals? So here we have a starting pressure, a starting volume, and we have a final pressure, and we're trying to find the final volume. So this is, again, the only things varying are pressure and volume. So once again, P2 over P1 equals V1 over V2. So if we solve for volume 2 equals volume 1 times P1 over P2. So volume 2 is going to be 10 liters. So it's 1 times 10 to the 6 pascals divided by 2 times 10 to the 5 pascals. 1 times 10 to the 6 divided by 2 times 10 to the 5 is just 5. So this will need to be increased to 50 liters. Here we have a balloon of oxygen, so it's sealed. So again, N is constant at 1 atmosphere at 300 degrees Kelvin, and it has a volume of 3 liters. If the balloon is cooled down to 200 Kelvin while still remaining at 1 atmosphere, what will its final volume be? So here, pressure remains constant. So we can replace pressure in this equation with a 1. And solve for other things. So I'll give you a little while to think about that. So again, P2 over P1 equals V1 over V2 times T2 over T1, but pressure is constant. So 1 equals V1 over V2 times T2 over T1. So if we solve for volume 2 equals volume 1 times T2 over T1. So 3 liters times 200 Kelvin over 300 Kelvin gives us 2 liters. We reduce the temperature by a factor from 3 by a factor of 2/3 to 2/3 its original temperature. If you keep the pressure the same, the volume will shrink by a factor of 2/3 as well. So those were some problems with the ideal gas law, just kinetic theory of gases. We'll leave all the problems on the homework and tests you'll be solving for pressure. But wanted to go over that. So thermodynamics. Thermodynamics is the full detailed study of the dynamics of heat and the conversion of heat to work in things like car engines, refrigerators, which move heat around, etc. So the first law of thermodynamics is just conservation of energy. It says heat added to a closed system goes into either the internal energy of the system and or doing work. It's just conservation of energy. Heat is energy. The heat added to a system equals a change of its internal energy plus the work done by the system. So you're not getting energy for free from nowhere or anything like that. So you can build a machine that takes heat from a high temperature reservoir, converts some of it to useful work, and dumps the rest to a low temperature reservoir. This is what's called a heat engine. And it turns out it will always look like this. It will always be hot, heat goes in, some of it becomes work, some of it gets dumped out to the low temperature reservoir. You can never have all of it become work. And that is related to the second law of thermodynamics, which is tied to the idea that it's impossible for heat to flow spontaneously from a colder body to a hotter body, and then it's sort of a maximum efficiency to heat engines. So no heat engine operating in a cycle can convert all thermal energy to work. 100% thermal efficiency is impossible. And there's a limit based on the difference in temperature between the high temperature and the low temperature. So you can have spontaneous heat moving from high temperature to a low temperature until you reach thermal equilibrium, but you do not spontaneously have heat moving from low temperature to high temperature. And the second law of thermodynamics is related to the concept of entropy. The idea that the disorder of the universe generally increases, and that any natural process will either require energy or entropy. It deals with what could happen spontaneously. Now, the third law of thermodynamics is that it is impossible to attain a temperature of absolute zero. Absolute zero is the lowest temperature there is. Some people also talk about a zeroth law of thermodynamics, which basically says temperature exists, but we don't need to worry about that here. So the coldest you can go is absolute zero, and you can never actually get there. And absolute zero corresponds to absolutely no motion, so it's impossible to achieve that state. So a summary, a humorous summary. First law of thermodynamics, can't win. Second law of thermodynamics, can't break even. Third law of thermodynamics, you can't get out of the game. So that's a sort of summary of the laws of thermodynamics. And the sort of inevitable consequence of the laws of thermodynamics is the heat death of the universe. Which is that everything will become cold and boring eventually. Now, it's not that you can't move heat from a low temperature place to a high temperature place. It's just that it requires work. So you can have a heat pump. A heat pump is something that takes heat from a low temperature reservoir, adds some work, and dumps that heat out at a higher temperature reservoir. And I am certain every one of you has used a heat pump on a daily basis. Because I assume you all have a refrigerator. That is a heat pump. It pumps heat out of the inside of the refrigerator into the outside world. Same with an air conditioner. It's a heat pump. It pumps heat out of your house into the outside. There's also something you can buy that's called a heat pump, which pumps heat out of the cold outside into your house and is often reversible and can work as an air conditioner. And that has the advantage of being, you get more heat than the work you put in. So if you have like electric heating, the work you put in just gets converted directly into heat. That's very easy and simple to do. But with the heat pump, you can be more efficient than that. Because you can pull heat from the outside. And that is a good thing. There are some issues. They don't work as well if it's colder out, things like that. It's complicated, but they're getting better, and there are ways you can make them even better. But so entropy is associated with so it turns out there's this idea of entropy that comes up in thermodynamics, and entropy is tied to the idea of whether or not a process can take place naturally. It's associated with the second law. So basically, if a process occurs spontaneously, or can occur spontaneously, either it is going from a higher energy state to a lower energy state, releasing energy, or it's going from a lower entropy state to a higher entropy state. So there are spontaneous processes that suck in heat, for example. But they increase entropy. So entropy is a measure of the disorder of a system. Most natural processes lead to an increase in disorder, an increase in entropy. The only way to decrease entropy is with energy. And to get that energy, it increases entropy somewhere else. So energy needs to be expended to decrease entropy. And since heat naturally flows from high to low, the entire universe will eventually cool down to a final common temperature, which will actually be quite cold because the universe is expanding, which will cause everything to be quite chilly. And the current average temperature of the universe is about 3 degrees Kelvin. So it's a few degrees Kelvin. But eventually everything will become cold and boring and black and dull, and that is the heat death of the universe. And that's the end of chapter 5. So some important equations, the conversions between temperature. We go from Celsius to Kelvin, you add 273. We go from Kelvin to Celsius, you subtract 273. We go from Celsius to Fahrenheit. You multiply by 1.8 and add 32. We go from Fahrenheit to Celsius, you subtract 32 and then divide by 1.8. So specific heat, the heat required to cause a change in temperature of a substance is mass times the specific heat capacity of the substance times the change in temperature. And if you want to find the change in temperature, it's the heat over mass times specific heat capacity. Latent heat, the heat required to change the phase of a substance, melt it or boil it, is mass times the appropriate latent heat. There's a latent heat of fusion for melting. There's a latent heat of vaporization for boiling. And pressure is proportional to NT over V. So P2 over P1 equals V1 over V2 times T2 over T1 times N2 over N1. But for all the problems I give you, N2 will equal N1, so this will just be 1. And the general equation is PV equals nRT. But I'm not going to bother giving you any problems where you actually need to use that equation. But it might help you understand where this is coming from. R is annoying because you have to write it properly for whatever units you're using. But yeah. And that is chapter 5. And I'm going to stop there for today. Any questions about anything? Your grades for your tests are up, but there's still someone who hasn't taken it, so I'm going to wait a little bit before handing it back. But you can see the scores you got up on Blackboard. Yeah, that is all. The general thing, the biggest thing that lost people points, was not answering questions. Because if you don't write anything down, I can't give you any points. Yeah. That is all. Have a nice day.